Hello everyone, my name is Roy and I am a PhD candidate at the Technion. Today, I will present my PhD research on artificial mind over matter. My advisors are Professor Avigdor Gal and Professor Akefet Ackerman. In my research, I tackled the problem of schema matching. Schema matching is a key component in data integration with the main incentive of providing correspondences between data elements, for example, database attributes. By way of motivation, consider the word cloud with the most common column headers extracted from thousands of web tables. As we can see, the frequent headers lack semantics and use extremely general terms. For example, a description can address a customer, it can address a store, it can address a product, and so on. Schema matching research has been going on for more than 30 years now, providing formal models, languages, algorithmic solutions, and empirical benchmarks. A matching process between two schemata applies matchers to generate similarity matrices. We can see here the formal model that we use throughout my research. To illustrate this schema matching model, we shall use the following example, representing two purchase order schemata. The basic procedure of schema matching applies matchers to generate similarity matrices. Matchers applied directly on a schema pair are called first-line matchers, and matchers applied over a similarity matrix are called second-line matchers. Here, we see two examples of matchers applied over our example schemata. On the top, an attribute named first-line matcher, termed term, is applied to generate a similarity matrix. For example, the similarity level between the two city attributes is 1, while the similarity level between order date and PO time is only 0.11. At the bottom, we see a second-line matcher that selects entries with values above 0.15. The motivation for my research is threefold. First, we observed that matching tasks are historically semi-automated. Taking that into account, we believe that recent advancements in the amounts and the availability of data, as well as the improvement of machine learning, may take the automation of schema matching one step forward. In the same breath, algorithmic matching is usually validated by human experts. Yet, we believe that it is not clear whether humans are superior decision makers. This is where my research comes into play, analyzing two parallel research questions as humans out and humans in. The goal of humans out is to use advanced techniques such as machine and deep learning to overpower human matching. Pursuing this goal, we offer two frameworks, learning to re-rank schema matches that was published in TKDE last year, and deep similarity matrix adjustment and evaluation, which I will present here in the main conference. Please come and check it out. Learning to re-rank schema matches aims to produce a better rank list of ranked matching results. To do so, we suggested to use matching predictors to represent similarity matrices as feature vectors. Then, we are able to train and use a learning to rank model. In this paper, we used a model term called Lambda Mart to re-rank a given list of top K schema matches and produce a better match list. In the paper, we offer a theoretical bound on the size of top K list of matches that assures with high probability an informative list. Please refer to our paper for additional details. The motivation for the adjust and evaluate algorithm is to capture relationships among matrix elements using deep neural networks that are not captured using human-designed heuristics. To do so, we designed a multitask neural network that both adjusts and evaluates similarity matrices. Prior to applying our algorithm, we trained a model over a training set of similarity matrices generated by state-of-the-art heuristic schema matches. The input for our algorithm is a similarity matrix, and its initial step uses a trained neural evaluator to evaluate the given matrix. Then, we adjust the similarity matrix using our pre-trained neural adjuster. And then we check whether the adjusted matrix is better using the same evaluator as we did before. We repeat these two steps until no improvement is obtained anymore and return the last matrix. In the paper, we provide conditions under which convergence and dominance can be guaranteed for this algorithm. Please join our session for more details, and please refer to the paper if you want to read about it. The goal for Humans In is to understand human matching. The main idea here is that even when moving forward towards automatic schema matching, humans' input will still be considered in the loop, for example, as labels in a learning task. Thus, we believe that by understanding and pointing out possible human disadvantages, it will be easier and reliable to use their input. One main issue to consider when experimenting with human matchers is the system which they use to produce the matching. Over the last 2 years, we have been experimenting with a tool called OntoBuilder. This study has yielded a data set containing over 1,200 matching decisions from over 250 human matchers. Yet, aiming to reach a larger crowd, we have created Incognito Match. Incognito Match was presented as a demo in SIGMOD 2020. Incognito Match is the first cognitive-aware crowdsourcing tool for matching. It gathers multiple valuable data from human matchers, including prior intelligence, confidence levels, decision times, and mouse movements. In addition, it allows researchers to control the matching context and to adjust the algorithmic assistance provided to the human matchers. Using the gathered data, we first aim to analyze the commonalities between human matchers and their algorithmic counterparts. As expected, humans also apply heuristic rules when matching schemata. Specifically, as we can see here in the figure, most human matchers in our experiment behave like a term matcher, matching elements based on the textual similarity. Next, we turned our efforts to try and understand whether human matching is consistent. In a perfect world, where human confidence is perfectly aligned with the correctness, this is what we expected to see. For example, we expect to see that out of the correspondences assigned with an average confidence level of 0.8, 80% are correct. However, when looking at the results, the picture is quite different. For example, only 40% of the correspondences assigned with a value with an average confidence level
of 0.8
are correct. So maybe humans are biased in the way they match schemata. In a work published in Prechi, we highlighted 3 main human biases. For example, the temporal bias, rooted in the metacognition literature, suggests that the more time humans spend on a correspondence, the less accurate and confident they become. Sounds a little surprising, doesn't it? One additional observation that we see here is that humans are usually overconfident, making their decisions less and less reliable. My main future directions follow the ideas outlined in my presentation. In terms of humans in, we aim to experiment with incognito match. In addition, we plan to use the highlighted biases in practice, aiming to create a collaboration model that uses human and algorithmic input conjointly. And in another direction, we aim to recognize expert matchers based on the way they behave. In terms of humans out, we plan to try and explore additional matching scenarios. First, we aim to explore matching without ground truth. In this setting, one cannot simply use supervised learning, and we have some interesting ideas to overcome this challenge. Finally, we started looking at an interesting scenario of personalized matching, where different people have different expectations from a matching result. Please stay tuned. Thank you very much for your attention. And if you have any questions or just want to talk to me, please feel free to contact me. Don't forget to come and check out our paper in the schema matching and mapping session at the main conference. Thank you very much again, and have a great day.